one that's online, so I am going to do multiple choice for the reactions portion. Again, just the first half of the test. The mechanisms, obviously, you're going to have to draw out just like you would on anything else. Yes.
You said multiple choice for what?
Just the reactions, just like the practice test that's up. So that's roughly about half the test, though. The reactions. There's lots of reactions.
So half that's multiple choice then?
Yeah, I think the first 100 points are all reactions, and they're all multiple choice, which is good and bad, right? Because all possibilities are there. I'm doing it because you really need to understand the regiochemistry and the stereochemistry. Those are the most important two things for each reaction. Is it Markovnikov or anti-Markovnikov? Is it syn or anti? Right? Because right there, just combining those two, how many options do you get? 4, right? Because you get Markovnikov and syn, Markovnikov and anti. You get anti-Markovnikov and syn, anti-Markovnikov and anti, right? So there's 4 possibilities, right there off the bat. And then I typically throw in just a 5th random crazy answer that you should never choose. And when you do, I go, what the hell were you thinking? But anyways, so make sure that not only do you know the product of the reaction, which you don't even really have to worry about that much, because I'm going to give you all the products, right? What you need to know is the regiochemistry and the stereochemistry for each of these reactions. Are you excited, Sean? Yeah. Okay. So, okay. With that in mind, let us look at another old test. Mechanisms and why questions.
Come on, man. Come on, really?
And there's some, is this an E double bond, is it E double bond? That type of stuff, just like some naming.
Can you give me some true or false?
Are we safe to just say resonance and all the
Yeah.
Can we restate the question?
You can restate it. I don't think you're going to get partial credit.
Would you get partial credit if you just wrote resonance?
You said it was going to go for a lot of things.
It depends on what the question was, right?
Everyone
So I'm going to post a key to this practice test also. So I'm going to skip the naming stuff. You can look at it and figure this out yourself. I want to get to the chemical reactions portion of it. But your test got stuff like this, like common names. You need to know that this is an allyl group. Identifying E or Z double bonds. There will be questions like this on your test. Is this E or is this Z? Kind of like the last test where there's is this S or is this R type of stuff. We talked about this stuff a little bit. Let's see if you guys remember. I'm going to look at question 4 here. Which of the following do you expect to be more or less dense than water? Right? So we barely mentioned this in class, but I know you guys all read your textbook, right, for the chapters. If you didn't, hell, you got a 50-50 chance on which one is right. But what is the rule for solubility and density? I guess this isn't solubility, this is density. So the first one is fluoropropane, second one is bromopropane, the third one is dichloroethane. So in terms of density, fluorinated molecules are almost always less dense, right? Bromo and chloro depend on how many are on there. If there's only 1 on there, they tend to be less dense. If there's 2 on there, they tend to be more dense, right? This is probably the most important one. You guys use methylene chloride in lab a lot, dichloromethane, right? So is dichloromethane usually which layer, top or bottom? Dichloro. Bottom, right? If you have more than 1 bromine or chlorine, you typically are more dense, right? So that's always a good thing to remember. If you use a methylene chloride, 95% of the time it's the bottom layer, right? Not always, but most of the time. All right, so let's look at some reactions, right? These are nice mixed reactions, and yours will be too. When I give you the multiple choice answers, I'm going to give you both elimination and substitution products as answers, right? And you would need to determine which one is correct. So let's go through these and talk about the major product. The hardest part in these is probably figuring out what type of mechanism is going through. Right? So how are we going to do that? We should always look at the substrate, and the reagents, the solvents help somewhat, but not necessarily too terribly much. So we have a secondary alkyl halide. We have azide as our nucleophile, N3. Is that a good, bad, or let's just go good or bad? Is it a good nucleophile or a bad nucleophile? Good. What are the only bad nucleophiles? Water and alcohols, right? If it's not one of those, the answer is it's good, right? So, what type of mechanism does this favor? SN2, right? It's not basic at all. The only things that we consider to be basic are the deprotonated alcohols or the bases that we looked at, right? None of the other nucleophiles are basic, right? So, if this isn't sodium hydride or an alkoxide, then you could assume it's going to do a substitution reaction. The alkoxides are the hardest ones, because these do substitution and elimination, and you have to decide which one. Pretty much all the other nucleophiles are only going to do substitution unless they are physically a base, sodium hydroxide or one of the alkoxides. So what's the answer here? What's it do? Yes, it's going to do an SN2 substitution. So if the bromine's up, then our incoming nucleophile is down. So the incoming nucleophile is down. So you get an inversion of chemistry, N3 goes on. Go with that. All right, the next one. What kind of nucleophile do we have? Bad, right? Which means this can undergo either an SN1 substitution or an E1 elimination, right? Since it's a secondary bromide. Those are our two choices. Substitution or elimination. It has to be SN1 or E1 because it's a weak nucleophile. The weak nucleophiles like the one mechanism, so they form the carbocation, right? There's a second clue to this problem, though. What is it? Heat, right? So when heat is present, what's favored? Elimination, right? So this is going to be an E1 elimination, right? So technically we form the carbocation. That carbocation is going to rearrange to the tertiary center. And then always with E1 eliminations, what type of elimination do we get? Hofmann or Zaitsev? Zaitsev, the more substituted double bond, right? So we end up with the wrong product on the key. Oh, no, that's the right product, because what do the instructions say? For the following substitution reactions. So the instructions, I tell you, they're all substitution reactions. So I should probably read my own instructions. So it has to go through a substitution reaction because the problem says so. Reading, right? Just like the owl, you got to read the instructions or whatever else. Without those instructions, it would have eliminated because of the heat. But notice where it is, right? Because it rearranged. Anytime you form a carbocation, it must rearrange. All right. Now we know they're all substitution reactions. We can proceed from there, right? What happens in this next reaction? We have sodium hydride and hexane.
Substitution.
What substitution? What happens here? So what's the product? Sodium hydride is defined as what? In the categories I gave you. Base only, right? Is it substituting? No, it's acting as a base. Bases go and find the most acidic thing they can and deprotonate it. Right? That's what bases do. What's the most acidic thing in that molecule? The OH. So what's it going to do?
Knock the OH off.
It's going to deprotonate it. That's what bases do. They deprotonate stuff. What is this? It's an alkoxide, right? What do alkoxides do to primary halogens? There's no reason that an intermolecular reaction can't take place intramolecularly, right? Inter means two different molecules, just like interstates go between different states, right? Intramolecular means that both the nucleophile and the electrophile are part of the same molecule. And what do we form? A 1, 2, 3, 4-membered ring. Did I leave out a carbon? I did leave out a carbon. So I'll say we're not making a 4-membered ring. We make it a 1, 2, 3, 4, 5-membered ring. The product is THF. This is the industrial prep for THF. This is how they make it. Right? Intramolecular SN2 substitution. Questions about that? All right. We're given H2S as the nucleophile, and we're specifically told that it's going through an SN1, right? Because normally sulfur prefers SN2 because it's a nucleophile only. What happens anytime that we have a small ring and we have a halogen 1 carbon away? Ring expansion, right? So this is bond's going to attack here, go from a 4-membered ring to a 5-membered ring, and then the sulfur is going to substitute. So we end up with the 5-membered ring with sulfur on there. Any questions about that? Sodium methoxide and acetone, we're adding it to a tertiary bromide. It says specifically in the instructions this is a substitution reaction, right? So what happens? Nothing happens. Why does nothing happen? We cannot do SN substitution at a tertiary site. It's too sterically hindered. If we weren't told that information, we would do an E2 elimination, but since we're told it's a substitution reaction, it cannot occur via a substitution reaction. Good? All right, the next section specifically says elimination reactions, right? So, we're given sodium hydride, a strong base, base only, right? We're given a cyclic bromide. Anytime we have a cyclic substrate and we're doing an elimination reaction, what do we always have to look at? What are the rules for... Okay, well, let's look at it this way. First off, sodium hydride. E1 or E2 mechanism. Always, 100% of the time, E2, right? It's a strong base. Strong anything go through the 2 pathways, right? So, it's only going to do E2. We have requirements for E2 eliminations. What are those requirements? The neighboring hydrogen and the leaving group have to have what relationship to each other? Anti-paraplanar. Right? Anti-coplanar. Right? So, what do we always have to look at for these ring structures? The chair. Okay? We need the bromine to be axial. This is our defining point. It's up and axial, so we put it up and axial. To the left, we have a methyl group that's down. It turns out that the down position to the left is also axial, which means the hydrogen here is equatorial. Is this hydrogen lined up properly? No, but this hydrogen is. So it doesn't eliminate to give the more substituted double bond because it's not lined up properly. Instead, it's only lined up to give the less substituted bond. Right? It eliminates away. And since we did nothing to this chiral center, it remains a chiral center. What about here? We're given ethanol. Does this favor E1 or E2? E1, right? The weak anything always favor the 1 mechanisms. So we're given an E1 mechanism. So what's going to happen first? Leading group's going to leave. We generate a secondary carbocation. Can we get more stable going left or right? Yes, which way? Left. So now we have a carbocation here. And anytime we have an E1 elimination, what's it favor? Zaitsev or Hoffman? Zaitsev. So do we eliminate to the left, to the right, or up? To the left, because that's going to give us a tetra-substituted double bond. To the right would give us tri-substituted, and up would give us di-substituted. So it's going to eliminate to the left, giving us the double bond over here. Good? All right, next one. We're given the base of potassium tert butoxide. This is a strong base or a weak base? What are the only weak bases? Water and alcohols, right? Just like they're the only weak nucleophiles. So is this strong or weak? Strong, right? So therefore it's going to go through what type of mechanism? E2, right? Anytime we go through an E2 mechanism on a linear substrate, we have to decide whether we're getting Zaitsev or Hoffman elimination, right? So, in order to determine that, what matters? Base size. So is this a big base or a small base? Big. So do we get Zaitsev or Hoffman? Hoffman. So we're going to get the less substituted double bond. Do we going to eliminate to the right or left or to the right? To the right, to give the less substituted double bond. Questions about that? All right, here we're given a substrate and we're just given a solvent and heat, kind of like on the homework that you did, right? What type of mechanism does this go through? E1, right? Because there's definitely nothing strong there. There's nothing there. We're just heating something up and it's decomposing essentially. It's eliminating. So we're going to, leaving group's going to leave. We're going to form a carbocation. Does that carbocation move? Yes. It's going to move right next door to the allylic, right? However, that's not going to change the outcome of the reaction whether you moved it or not. So here's our carbocation. There's no hydrogen here we can pull off because that's sp2 hybridized. It's not going anywhere. So we can only pull off this one, right? So we ended up with the conjugated double bond. Questions about any of those? Okay. All right, why type questions? Your favorite? They have this. Okay. It says a student performed the following reaction and obtained a mixture of two products. So here's the reaction conditions. Sodium methoxide with methanol as the solvent, and they got a mixture of the SN2 substitution and the SN1 substitution. Is everybody okay with the two products? Let's see where they come from. Right, this is an SN2 substitution. We inverted the center. This one migrated. Right, the only way you can do that is going through an SN1. And it's reasonable to get both of them, and they did. So the first part says, how could the student modify the reaction conditions to get a greater quantity of A? Now be specific. So an example of an incorrect answer would be they could change them. Right? That is not specific. Although it technically does answer the question. Okay, there we go. What can we do?
I'd say change the solvent because it's going through Savolysis.
It's not going through Savolysis because Savolysis means there's only a solvent there, but it is going through an SN1. Right? So this is the SN2 product. If we want to favor SN2, instead of using a polar protic solvent, we can switch to a polar aprotic solvent, which favors the SN2 mechanism. So that's a good solution, and I like it. Right? So that's what I also have. Use a polar aprotic solvent instead. Right? So changing the solvent. Okay, part B says, how could they modify it to only, or not to only get, but to increase the quantity of B? You need to see the reaction again? How can we get more B? Yeah, remove the sodium methoxide from it, right? Remove the strong nucleophile. Run a pure Savolysis reaction. We'll get the same product, right? We just get rid of the strong nucleophile. So that's exactly what we should do. Get rid of the sodium methoxide and run it in pure methanol, right? Remove the strong nucleophile from the equation. So we can manipulate it either way. Right? We can make it more SN2-like by changing the solvent, or we can get rid of the strong nucleophile altogether and get more of the SN1 product. Questions about that? You guys know you love those type of questions. All right. Kind of got the answer up there. So it says the rate data for the following reaction shows first order, I'm guessing that's supposed to say in, first order in substrate concentration and first order in nucleophile concentration, meaning it is second order overall. Propose a mechanism for the following transformation. Right? We know it's SN2 based on what it was said. It's second order overall. That is what the definition of an SN2 is. It depends on both substrate concentrations. Normally in an SN2, what do we do? The nucleophile, which is acetate in this case, comes in and displaces the halogen, and the halogen leaves. However, does that give us the indicated product? No. So there's our nucleophile, acetate. If we run the reaction like we've normally looked at it, and we have this come in and attack and the bromine leave, my markers are dead. Ooh, that works.
Good color choice.
Anybody want Chris's extra credit points from
Got a little blue in here.
This is what we would get in a normal SN2, right? Yes? Everybody agree? So 1, 2, 3, 4, 1, 2, 3, 4. We formed a bond between oxygen and carbon too. But that is not the indicated product, right? Obviously it has something to do with this double bond here. And if we think about it, if we got rid of the bromine through an SN1 type mechanism, then this leaving group could leave, right? We would form the carbocation which has resonance. And if the nucleophile attacks this carbocation, then we get the product. But we can't do this because this is an SN1, and the rate data tells us that it's an SN2. So what have I always told you? If you can't do things in 2 steps, do them in 1 step. So we're essentially going to draw those arrows, but in the same fashion. Right? So the proper mechanism here, and this is still technically an SN2, is as follows. The negative bond, or the negative attacks the double bond. The double bond collapses over, and the bromine leaves, right? Which gives us the desired product, right? And this is still all happening at once. 2 things involved. This is the SN2 mechanism, right? And it's just as likely to occur in this fashion as the direct replacement. Actually, this would be the major product of this SN2 reaction. So everybody follow the logic on how to get there.
If we do an SN1, we'll do the SN1.
Sure. It's to show that even SN2s have resonance, right? It's not direct resonance structures like here where we physically draw them, but anything that has, you know, a leaving group with a double bond next to it is capable of resonance. This is SN2 type resonance, right? I got papers everywhere. The next one you have to circle stuff, so I can't really put it up, so I'm looking for the unfilled out version. Okay. Circle the better nucleophile from each pair. So let's look at pair A. We have potassium butoxide versus potassium ethoxide. Which one's the better nucleophile and why? We'll answer the why question here, so it doesn't ask it. But which one would you circle? First one or second one? Second one. That'd be correct. But let's talk about why. Smaller nucleophiles are better because in SN2s they can get in there better and attack. Okay. Sodium cyanide versus sodium bromide. What? Cyanide, why? But this is purely about nucleophilic, right? But if you look back at the order of the nucleophiles I gave you, cyanide is a better nucleophile. Right? You can draw resonance structures for a cyanide, and anytime you have resonance stabilization, it's better than just having it isolated on a single atom, even if it's as big as bromine. Right? Sodium fluoride versus triethylamine. Triethylamine. Remember, fluoride F- is in the worst category. Right? It's over there with water and the alcohol. So triethylamine, even though this is only a medium nucleophile, is still better than sodium fluoride. Any questions about that? All right, the next one just asks you to draw line structures for 2 solvents. Right, I gave you a whole bunch of solvents. All their structures are fair game. Right, in this case, I asked for toluene and DMF. Anybody take a shot? What's toluene? Good. Benzene with a methyl on it. Right? So there's toluene. What's DMF stand for? Dimethyl is right. Dimethyl formamide. Dimethyl formamide. Yeah, look over those. Okay.
Just the ones you gave us, right?
Mm-hmm. You get a lot. All right. Mechanism. In the mechanisms that I give you, you have to give me whatever product I show. Whether it's the major product or not, you need to push the arrows to get to whatever it is. So if I give you a minor product, still push the arrows to get to the minor product. One thing you should always look at with these is, based on the product, determine what type of mechanism it went through. Did it go through E1, E2, SN1, SN2? So it's going to help with the mechanism, right? So which one did this go through based on the structure? E1. Right? We know it's an E1 because, well, we know it's an E because we made a double bond. It's elimination. And then if we look, we started with 2 carbons on here and none over here, and we ended up with 1 and 1. So it rearranged. You can only rearrange in carbocation-based mechanisms, right? So this definitely went through an E1. Anytime there's an acid present, what is always 100% step 1? Protonation. So we're going to protonate first. I'll put the mechanism up in a second. And the reason we need to protonate first is to turn that bad leaving group into a good leaving group, right? Once it's a good leaving group, then it's going to leave, right? Once it leaves, we generate a carbocation. Carbocations rearrange, and once it rearranges, then it's going to eliminate to form the more substituted double bond. So, mechanistically, I think in the answer key I use sulfuric acid, but in reality we should be using H3O+, right, anytime there's acid in water. First step is always protonation. The lone pair picks up a proton, those 2 electrons go on to the oxygen. We took a bad leaving group and made it a good leaving group, and now it leaves. We generate a secondary carbocation. If we move over here, it's primary. If we're able to move over here, it would be tertiary. So we get a methyl shift. Since the methyl group is taking its electrons with it, we start from the center of the bond and move it to the carbocation. This carbon is now deficient a bond, right, because it moved its bond over. Once we have the carbocation, right, we're always going to eliminate from the more substituted double bond. Here would give di-substituted, here would give di-substituted, here would give tetrasubstituted. We need those electrons for the double bond. They got to come from somewhere. They always come from the neighboring hydrogen. So what we're pulling off is this neighboring hydrogen. These 2 electrons are what are going to be the 2 electrons of the double bond. Water is the only thing that's basic in this acidic solution. So water is going to come in, pull off this hydrogen. These electrons are going to collapse down to form the double bond. Questions about that? All right, some reactions. Lots of reactions. Let's switch to the one with the key. So that was essentially the Chapter 9 portion of the test. Right? Now we'd be switching into the Chapter 6 portion. And there's a whole lot more reactions in the Chapter 6 portion. All right. Let's go through them. We know that Chapter 6 is all about the reaction of alkenes. So in every one of these reactions, we're going to be doing what? Converting the alkene into something else. So finding the reactive center shouldn't be hard. It's the alkene. Right now the question is what happens to it, and this is going to be based upon the conditions. And sometimes we're going to have to worry about stereochemistry and regiochemistry. Sometimes we won't. Most of the time we will. So, anybody know the name of this first reaction? That's what it does. What's the name of it? It's named after God. 2 guys. Simmons-Smith. Right? This is the Simmons-Smith cyclopropionation reaction. It makes cyclopropane. Right? So all we do is take the double bond and turn it into a cyclopropane. Right? These are milder conditions than the diazomethane reaction that we looked at. Not much to do in that reaction but memorize that that's Simmons Smith and make cyclopropane, right?
We didn't do the mechanism, right?
No. Remember that we called it magic.
Right.
Yeah.
I'm gonna write.
I don't know the mechanism for that reaction.
Seriously?
Yeah, seriously.
You know everything.
Not that. I don't know if anybody knows it very well, because nobody really knows what copper does. They just know you've got to have copper or it doesn't work. So anytime you don't know why something doesn't work, it's really hard to come up with a mechanism on how it's involved.
Do the people who drew-
I'll see if I can look it up. I'll bring it in for you.
Do the people who made it know?
What?
I'm assuming they were mechanism.
No. Very unlikely. So there's two fields of organic chemistry. There's synthetic organic and there's physical organic. Synthetic organic chemist is what I was. We didn't care how the hell A turned into B, just that it did. Right? And then there's physical chemists who spend their whole careers trying to explain why A turned into B. Right? So while synthetic chemists are making new drugs, curing the world, the other people are going, well, here's how that might have worked. But nobody cares, right? All they care is that it did work. So anyways, if somebody was developing this new reaction, I developed a new reaction in grad school, and what you do is you just try random stuff, right? You get acidic conditions that kind of works, and then you change it. So
If you don't care why it works, why do you
You
keep
have a-
asking us the why question?
you have a basic understanding of how it works, right? But then for something like this, where they added copper 1 chloride, I'm sure they tried all kinds of catalysts, right? And this is the catalyst that worked the best, right? Why? I don't know. The reaction I did in grad school, I screened like 40 different catalysts. I took pretty much every catalyst we have in our lab and I tried it and saw which one worked the best. And it was changing stuff like gold 3 chloride versus gold 1 chloride versus scandium versus whatever. You just go through them and you know basically how the reaction works. There's a coordination between the catalyst and the double bond that gives a partially positive charge. The nucleophile comes in and attack. But why copper 1 works better than chromium 1? It does, right? But specifically, would you predict that before a reaction? Hell no, right? So, nobody cares. At least I don't care. There are a whole branch of people that care, but.
When it comes to all these reactions, you said this is going to be like multiple choice, right?
All right. HBr. You should recognize that it's going to add a hydrogen and a bromine to the double bond. The only question is the regio and the stereo. So regio, we should notice that we're given peroxides, which tells us the regiochemistry is what? Anti-Markovnikov. Right? So it's going to be anti-Markovnikov and anti-Markovnikov. Do we care about the stereochemistry?
How do we know that?
No.
Because HBr and peroxides are the conditions for anti-Markovnikov addition. Right? Markovnikov additions is just HBr. The peroxides, remember, makes the free radical and goes anti. So we didn't care about the stereochemistry here, just the regiochemistry. So you should recognize this is anti-Markovnikov. So the bromine adds to which carbon? The more or the less substituted? The less substituted. So there's our product. Good? All right, you're given osmium tetroxide. Right? The second step is just part of that first reaction. Who cares? Right? Osmium tetroxide. You got to remember, what does that reaction do? Nope, that's ozone. It makes a diol. It makes a diol. Right? Is there any regiochemistry issues with a diol? No, you're putting an OH on both carbons, so the regiochemistry is always the same. What does matter in this reaction? The syn addition, right? The stereochemistry. And we have to remember that osmium tetroxide adds in a syn fashion, which means the two OHs need to be on the same phase. They could either be both down or both up. But that's the key to remember. Because I'm going to put on the test both syn and anti, and then 3 other crazy answers, right? And you need to remember the syn addition. The syn addition is what's important there.
So you're not going to give us a whole bunch of answers and all the shit.
Oh yeah, of course. For this one, I would probably give you the syndiol, the antidiol, the epoxide, and the ozonolysis product, right? Which are all real type answers. And then one crazy one, just to see if you guys choose it.
Yes.
With like Superman on
Do
it.
you get extra? Do you give extra points for that?
All right, next one. HBr on its own, right? All these reactions are addition reactions. We're adding something to the double bond. In this case, we're adding a hydrogen and a bromine. What matters here is the regiochemistry. How does HBr add? Makhovnikov. So is the bromine going to go to the more or the less substituted carbon? The more. Does stereochemistry matter here? No. We're adding it through a carbocation. We're going to get a racemic mixture. Stereochemistry is unimportant. Right? So we get the more substituted double bond. Good? All right. H2 platinum on carbon, or palladium on carbon. We only know one reaction that involves hydrogen gas. What's it do? All these reactions take the reagent and add them across the double bond. In this case, we're adding H2, so to each side we add hydrogen, right? So regiochemistry is obviously not an issue, because both sides get a hydrogen. What is important? Stereochemistry. How does H2 add? Syn. Remember, it reacts on the surface of the metal. It adds both hydrogens at the same time. However, in this problem, do we generate a chiral center here? No. Do we generate chiral centers here? No. There's already one hydrogen. We're adding more. We'll have two hydrogens. So in this case, in this one, it wouldn't matter, because there is no stereochemical outcome. But in other problems, it might. You need to remember that H2 adds in a syn fashion. On this problem, it doesn't matter, because we don't generate any chiral centers. Therefore, don't need stereochemistry. All right, the next one. Right? B2H6 followed by hydrogen peroxide workup. What does this add? This is anti-Markovnikov addition of water. Right? Think about every product that we've ever formed in this chapter. They're all normal functional groups. Right? The products are always a normal functional group. It's an alcohol. It's a halogen. It's something like that. Right? Do you know borane-based functional group? No, right? So you're always going to make something normal. If your product isn't normal, it's not right, right? So this adds water anti-Markovnikov. So, in this reaction, does stereochemistry matter? No, because we're not generating chiral centers. But in other reactions, it will. What is this? So the regiochemistry here is anti-Markovnikov. What's the stereochemistry? What? This is syn, right? So this is anti-Markovnikov and syn. So the hydrogen and the OH would add to the same face. Again, in this example, it doesn't matter because there's no stereochemistry. But if we were given something like this, right, then the product is this, right? Anti-Markovnikov and syn. You need to know the stereochemistry.
That's hydroboration, right?
Hydroboration oxidation. Yes. All right. This looks like a halogenation reaction, but we're also adding water, right? So this is one where we put the chlorine on one carbon and the OH on the other. In terms of regiochemistry, is it Markovnikov or anti-Markovnikov? Markovnikov, meaning the alcohol goes to the more substituted carbon. What about stereochemistry? How does this reaction work? It forms that chlorine ring, right? and then water comes in and attacks to open that chlorine ring. So if the chlorine's up, where's the water going to come in from? Down. So what's the regiochemistry? Anti. So it's Markovnikov and anti, right? So here I have drawn the OH down, which means the chlorine has to be up. I could have drawn the OH up, that means the chlorine would have to be down, right? You get a racemic mixture. So this is Markovnikov and anti. What about the next reaction, MCPBA? What's that make? It's a peracid. What do peracids make? Epoxides. Right? This is going to make an epoxide. Remember, this is the mechanism with all the arrows in that one step. Right? It's a single step reaction. So what type of stereochemistry do we get? Syn or anti? Syn. If it all happens at the same time, you don't have time to switch faces. Right? So this is syn addition, which means the epoxide is either going to be up or it's going to be down. Right? So we either need it up or down. Doesn't matter which one. We make the epoxide. What are the next set of conditions there? This is how we add water in a Markovnikov fashion without rearrangement. Right? However, is our nucleophile water? No, it's methanol. So we're going to add methanol in a Markovnikov fashion, but without the possibility of rearrangement. So where does the methanol go? To the more substituted carbon, Markovnikov. Right? So it's going to add to the more substituted carbon. Now, the reaction I gave you in class, this orange doesn't erase very well. I gave you this reaction, in which case it would go here, Markovnikov without rearrangement, right? But in this case, the Markovnikov is the tertiary center, right? So it's still a Markovnikov reaction. What about the next one? These are our standard hydration conditions, right? This is just adding water. Water under acidic conditions is always going to add in what fashion? Markovnikov. Yes, that's correct. Right. So we have two choices. We can form a secondary carbocation or a secondary carbocation. However, this secondary carbocation can do what? Rearrange, and it does. So it's going to rearrange to the tertiary center, and that's where our water is going to attack. So you get two possibilities here. Right? If it formed the carbocation here, is it going to rearrange? Nope. So it would give the product on the right. However, if it forms a carbocation here, it would rearrange. And since these are both secondary, they're both equally as likely to occur. All right, questions about any of those? All right? You might have a mini little synthesis type problem. So here, you're given 2-bromo, actually it's 1-bromo, 2-methyl cyclohexane, and you're asked to make the anti-diol. Okay? How are we going to do it? Well, a lot of times with synthesis problems, it's better to work backwards. And to tell people that you're moving backwards, what you do is you use a retrosynthetic arrow. which looks like the following. Instead of a single line, you have two lines. This tells people you're not moving forward, you're moving backwards. So the question is, how do we make antidiols? You only know one way. What is the one way you know how to make them? You know how to make them from an alkene. How do you make them from an alkene? This was, you make the epoxide, and then you open the epoxide with acid. Remember, we learned how to make two different types of diols. Antidiols, which are MCPA followed by acid, or syndials, which is our osmium tetroxide. Can we make this alkene from that bromine? Can we go this way? Sure, it's just a E2 elimination. However, is this product the Hoffman or the Zaitsev? It's the Zaitsev. If this can eliminate here or here, here's more substituted. How do we prefer Zaitsev? We use big or small bases? Small. So we could use something here like sodium hydride in hexane. Right? So this would be our two-step process. We would treat it with sodium hydride and hexanes first to eliminate it, E2 elimination. And then we could make the epoxide and open it to get to the trans-diol. Right? So putting a couple reactions together. What about here? This is another synthesis. Right? Again, the two arrows does not mean it's two steps. It just means there are steps. Right? It could be 2, it could be 1,000. Right? 1,000 would be mean. What's the only way we know how... Okay, first off, what's the relationship between this bromine and that methyl? They're 1-2, right? Which 1-2, anytime we have a 1-2 relationship, does that suggest that we used a Markovnikov or an anti-Markovnikov? All right, let's go about it a different way. What's the only way we know how to put bromines, or we know two ways to put bromines on molecules. Right, the very first reaction we ever learned, Br2 and UV light. But if we treated this with Br2 and UV light, where would the bromine go? With the methyl. It's selective for the tertiary position. So that way we can't do it. However, we have to do that reaction first. Why? How do we know that the first step of this reaction is Br2 and UV light to form the tertiary bromide? How do we know that? What is the starting material, classification-wise? What would we call it? An alkane, right? Carbon single bonds, alkane. How many reactions of alkanes do we know? Give you a hint. It's 1. Right? That's the only reaction we know for alkanes. Okay? So if we're starting with an alkane, this is the only thing we could possibly do. Right? We have no other choice. Anytime your starting material is an alkane, that is step 1. Because it's the only reaction we know for alkanes. Now the question becomes, how do we move it from that position to 1 carbon over? How are we going to do it? Well, we can do 2 things with halogens. What are they? We can substitute them and eliminate them. Does substituting this help us in any kind of way? No. That leaves one choice. What is it? Elimination. Following Zaitsev elimination, it would give us this double bond. Right? What do we need to do now? we need to add HBr, right, to get to the product. But do we need to do it Markovnikov or anti-Markovnikov? Anti. So what are the conditions for anti-Markovnikov addition? HBr in peroxides gives us the product. Right? So you can reason your way through the synthesis problems. We only know one thing we can do with an alkane. Once we've done that, now we can look at it and go, well, we can either substitute it or eliminate it. Substituting it doesn't do us any good, we should eliminate it. And once we're here, you should recognize that it's only one step anti-Markovnikov addition of HBr. All right, the next question wanted a mechanism. This is halogenation. Notice the anti-stereochemistry, right? What's the mechanism for this reaction? What do you form first? You form that bromonium ring, that three-membered ring with the bromine in it that's positively charged. Remember, we formed that because the double bond attacks the bromine attacks the double bond, and the other bromine leaves. So the first step always has those three arrows. Bromine attacks, double bond attacks, other bromine leaves. And then the way we get the anti-stereochemistry is that the bromine comes in and attacks the more substituted carbon. In this case, they are the same, so it doesn't matter. But if they weren't the same, it always attacks the more substituted carbon. Why? These reactions have two types of control. What are the two types of control? Steric and electronic. In this case, what's it following? Electronic. It's attacking the more positive of the two carbons. Again, in this case, it's equal. If the bromine there is down, the new bromine coming in must be up, right? I made such a mess, I don't know if there's anything else. I think that was the end of the test.
If you had a methyl on one side, it would go to one of the methyl, right?
What?
If there was a methyl group on one, it would go to the methyl group.
Mm-hmm. So if you had this situation, the next arrow you would draw is attacking the more substituted position, electronic control. And these electrons going on to the bromine, and that inverts that whole center. So the methyl group that was up is now down, and this bromine is up. All right. Any questions about what we just looked at? Do you at least have an understanding of what's going to be expected of you, whether you get there or not? Okay, I got to take a bathroom break for a second, and then I will